Hello friends, this is a video lecture. We are the final year student, Department of Electronics and Communication Engineering from Assam Don Bosco University. We are going to discuss about optical detectors and their various types and its application. So let's begin with introduction of photodetectors. The detector is an essential component of an optical fiber communication system and is one of the crucial elements which dictate the overall system performance. Its function is to convert the received optical signal into an electrical signal, which is then amplified before further processing. The role the detector plays demands that it must satisfy very stringent requirements for performance and compatibility. A photodetector is a device which absorbs light and converts the optical energy to measurable electric current. Detectors are classified as thermal detectors and photon detectors. Now begin with the thermal detectors. When light falls on the device, it raises its temperature, which in turn changes the electrical properties of the device material, like its electrical conductivity. For example, thermopile, pyroelectric detector, etc. And the second one is photon detectors. Photon detector work on the principle of conversion of photons to electrons. Unlike the thermal detectors, such detectors are based on the rate of absorption of photons rather than on the rate of energy absorption. Photons detectors in terms of the technology could be based on vacuum tubes and semiconductors. The example of vacuum tubes is photomultipliers and the example of semiconductors is photodiodes. Now, the following criteria define the important performance and the compatibility requirements for detectors, which are generally similar to the requirements for sources. The first one is high sensitivity at operating wavelengths. The first generation systems have wavelengths between 0.8 and 0.9 micrometer. However, considerable advantage may be gained at the detector from second generation sources with operating wavelengths above 1.1 micrometer, as both fiber attenuation and dispersion are reduced. The second one is high fidelity. To reproduce the received signal waveform with fidelity for analog transmission, the response of the photodetector must be linear with regard to the optical signal over a wide range. The third point is large electrical response to the received optical signal. The photodetector should produce a maximum electrical signal for a given amount of optical power. That is, the quantum efficiency should be high. And the fourth point is short response time to obtain a suitable bandwidth. The response time of the optical detector should be minimum to obtain a suitable bandwidth. The fifth point is a minimum noise introduced by the detector. Dark currents, leakage currents, and shunt conductance must be low. Also, the gain mechanism within either the detector or associated circuitry must be of low noise. The sixth point is stability of performance characteristics. Ideally, the performance characteristics of the detector should be independent of changes in ambient conditions. However, the detectors currently favored have characteristics which vary with temperature, and therefore compensation for temperature effects is often necessary. And the seventh point is small size. The optical detector should very small in size. The number 8, low bias voltages. Ideally, the detector should not require excessive bias voltage or currents. In the number 9, high reliability. The detector must be capable of continuous stable operation at room temperature for many years. So the reliability should be high. And the last one is low cost. Obviously, the economic considerations are often of prime importance in any large-scale communication system application. Now move to the optical detection principles. The basic detection process in an intrinsic observer is illustrated in these figures shown here. In the figure, it shows a PN photodiode. This device is reverse biased and the electric field developed across the PN junction sweeps mobile carriers, which are holes and electrons, to their respective majority sites, which is PN n-type material. A depletion region or layer is therefore created on either side of the junction. This barrier has the effect of stopping the majority carriers crossing the junction in the opposite direction to the field. However, the field accelerates minority carriers from both sides to the opposite side of the junction, forming the reverse leakage current of the diode. Thus, intrinsic conditions are created in the depletion region. Now, as shown in the figure A, here you can see a photon incident in or near the depletion region of this device, which has an energy greater than or equal to the band gap energy. This is the band gap energy shown here. Eg is the band gap energy here of the fabricating material, that is HF. HF which is greater than equal to energy gap. HF is the incident photon, will excite an electron from the valence band into the conduction band. Here you can see the excitation of electron from valence band to conduction band. Now this process leaves an empty hole in the valence band. And is known as the photogeneration of an electron hole pair. As shown in the figure B, carrier pairs so generated near the junction are separated and drifted under the influence of the electric field to produce a displacement by current in the external circuit in excess of any reverse leakage current. And in the figure C, photogeneration and the separation of a carrier pair in the depletion region of this reverse bias PN junction is illustrated. The depletion region must be sufficiently thick to allow a large fraction of the incident light to be absorbed in order to achieve maximum carrier pair generation. However, since long carrier drift times in the depletion region restrict the speed of operation of the photodiode, it is necessary to limit its width. Thus, there is a trade-off between the number of photons absorbed and the speed of response. Now move to the parameters of the these are the points I have already mentioned. Here see the basic detection process in intrinsic observer, which shows an PN photodiode, which I have already mentioned. These are the points I have already discussed. Now move to the parameters of optical detectors. There are two parameters: quantum efficiency and responsivity. Now let's begin with quantum efficiency. The quantum efficiency is denoted as nu, and which is defined as the fraction of incident photons which are absorbed by the photodetector and generate electrons which are collected at the detector terminals. And it is given by number of electrons collected by number of incident photons, and mathematically it is equal to Re by Rp, where Re equal to rate of electron collected in the terminal and Rp equal to rate of incident photon. One of the major factors which determines the quantum efficiency is the absorption coefficient of the semiconductor material used within the photodetector. The quantum efficiency is generally less than unity, as not all of the incident photons are absorbed to create electron hole pairs. Furthermore, it should be noted that it is often quoted as a percentage. For example, a quantum efficiency of 75% is equivalent to 75 electrons collected per 100 incident photons. Finally, in common with the absorption coefficient, the quantum efficiency is a function of the photon wavelength and must therefore only be quoted for a specific wavelength. Now, responsivity. The expression for quantum efficiency does not involve photon energy, and therefore the responsivity R is often of more use when characterizing the performance of a photodetector. The performance of a photodetector is determined by the parameters which is called responsivity, and it is denoted by R. The definition is, it is defined as the ratio between the average current generated in the detector and the average optical power incident on the detector, and it is expressed as R equal to IP by P naught, and its unit is ampere per watt, which is equation number 1, where IP is the output photocurrent in amperes and P naught is the incident optical power in watts. The responsivity is a useful parameter as it gives the transfer characteristic of the detector. The relationship for responsivity, equation number 1, may be developed to include quantum efficiency as follows. Here we will derive an equation, the relationship between the responsivity and the quantum efficiency. The energy of a photon E is equal to hf. Thus the incident photon rate Rp may be written in terms of incident optical power and the photon energy as Rp equal to P naught by hf, which is equation number 2. And the electron rate is given by Re equal to nu Rp, which is equation number 3. Now substituting from equation number 2, we obtain Re equal to nu P naught by hf, which is equation number 4. And therefore the output photocurrent is Ip equal to nu P naught E by hf, the equation number 5 here, and where E is the charge on an electron. Thus from equation number 1, the responsivity may be written as R equal to mu E by hf, which the equation number here is 6. Equation 6 is a useful relationship for responsivity which may be developed a stage further to include the wavelength of the incident light. The frequency f of the incident photons is related to their wavelength lambda, and the velocity of the light in air c is given by f equal to c by lambda, and it is given by equation 7. And finally, substituting into equation 6, a final expression for the responsivity is given by R equal to mu E lambda by hc. Now it may be noted that the responsivity is directly proportional to the quantum efficiency at a particular wavelength. So this is the relationship between, this is the equation finally we got, and this is the relationship between responsivity and the quantum efficiency. Now the ideal responsivity against wavelength characteristics for a silicon photodiode with unit quantum efficiency is illustrated in this figure A, also known as the typical responsivity of a practical silicon device. In the figure B, however, compares the responsivities and quantum efficiencies of the photodiodes based on silicon germanium and indium gallium arsenide ternary alloy. It shows the lower values of responsivity of 0.45 and 0.65 ampere per watt at signal wavelengths of 0.90 micrometer, here 0.90 micrometer, and 1 ampere per watt at signal wavelength of 1.30 micrometer respectively. For silicon and germanium photodiodes, high responsivity values of 0.9 and 1 ampere per watt at signal wavelength at 1.30 micrometer and 1.55 micrometer respectively. For the photodiode fabricated from indium gallium arsenide alloy can also be observed. Moreover, nearly 90% quantum efficiencies can be obtained for both the indium gallium arsenide and silicon photodiodes. Now, long wavelength cutoff. It is essential. The long wavelength cutoff is essential when considering the intrinsic absorption process that the energy of incident photon is greater than or equal to the band gap energy Eg of the material used to fabricate the photodetector. Therefore, the photon energy, which is given by Hc by lambda greater than equal Eg, and the lambda can be obtained as less than equal to Hc by Eg. Thus, the threshold of detection, commonly known as the long wavelength cutoff point delta C, and which is given by Hc by Eg. The expression given in equation 3 allows the calculation of the longest wavelength of light to give photodetection for the various semiconductor materials used in the fabrication of detectors. Now, types of photodetectors. Semiconductor, there are two types of photodetectors. First one is semiconductor photodiodes without internal gain, and it has two types. First one is the PN junction photodiode, and second one is the PIN photodiode. And the main second part is semiconductor photodiodes with internal gain, and it has only one type, which is avalanche photodiode. Now I start with PN junction photodiode, which is also a photodiode without gain. In this figure, it shows a reverse bias PN photodiode with both the depletion and diffusion regions. The depletion region is formed by immobile positively charged donor atoms in the N-type semiconductor material and immobile negatively charged acceptors atoms in the P-type material. When the mobile carriers are swept to their majority sites under the influence of the electric field, the width of the depletion region is therefore dependent upon the doping concentrations for a given applied reverse bias. That is, the lower the doping, the wider the depletion region. The photons may be absorbed in both depletion and the diffusion regions. Here you can see this is the depletion region and this is the diffusion region, and this is from here to here, this is the absorption region. Photon is incident here. This is the electric field. The absorption region's position and width depend upon the energy of the incident photons and on the material from which the photodiode is fabricated. Thus, in the case of the weak absorption of photons, the absorption region may be extended completely throughout the device. Electron-hole pairs are therefore generated in both the depletion and diffusion regions. In the depletion region, the carrier pairs separate and drift under the influence of the electric field, whereas outside this region the hole diffuses towards the depletion region in order to be collected. The diffusion process is very slow compared with drift and thus limits the response of the photodiode. These are the points I almost mentioned. Here you can see when a photon of energy greater than the band gap energy of the semiconductor material, and that is incident on or near the depletion region, it excites the electron to the valence band to conduction band. These are already mentioned. Now this is the this is the diagram of typical PN photodiode output characteristics. For the reverse biased PN photodiode are illustrated in this figure. The different operating conditions may be noted moving from no light input to a high light level. Here you can see this is the characteristic and this is the high light level characteristic, and low light level, and last one is dark current, actually no input light. Now my friend will take over from me and he will explain other types of photodetectors and their advantages and limitations. PN junction photodiode disadvantages. Photodiode is generally incident on the P side. Now if the carrier is generated on the P side where there is no electric field, because most of the electric field is generated in the depletion region. So the carrier generated in the P side has to diffuse to depletion region so that they can drift towards the N cycle. Because of the diffusion process, the response time of the photodetector is poor. If we want the response time to be very fast, the diffusion process should be minimized. For this to happen, the width of the PN layer should be minimized. If we want the carrier to be generated in the depletion region, the depletion layer width should be made larger. And the last point, therefore, to increase the efficiency and responsivity of a photodetector, firstly, the effective length over which the absorption takes place should be maximized and the depletion layer width should be independent of the biasing voltage. Now, the PIN photodiode. To overcome the disadvantage of the PN junction photodiode, we use the PN photodiode. It is also the type of semiconductor photodiode without internal gain. In order to allow operation for longer wavelength where the light penetrates more deeply into the semiconductor materials, a wider depletion region is necessary. To achieve this, the N-type material is doped so lightly that it can be considered intrinsic, and to make a low resistance contact, a highly doped N-type or N plus layer is added. This creates a PIN or PIN structure as may be seen in figure, where all the absorption takes place in the depletion region. You can see this absorption is taking place in the depletion region. This is different in case of PN diode from the PN junction photodiode. So the working includes the diffusion components of a PN photodiode can be reduced by decreasing the width of the PN N side and increasing the width of the depletion layer. To achieve this, a layer of a semiconductor which is very lightly doped without almost intrinsic is inserted at the PN junction. Such a structure is called PIN photodiode. As the middle layer is intrinsic in nature, it offers a high resistance and therefore most of the voltage drop appears across it. Thus a strong electric field exists in the middle eye region. This is the eye region. Such a configuration results in the drift component dominating the diffusion component and therefore the response time is very good. So these are the points which I have discussed. You can see. So next we have the figure shown are the two types of silicon photodiode for operation in shorter wavelength band below 1.09 micrometer. Figure A is the structure of front illuminated silicon PIN photodiode. The front illuminated photodiode, when operating in 0.8 to 0.9 micrometer band, requires a depletion region of between 20 and 50 micrometer in order to attain high quantum efficiency, typically 85%, together with fast response, less than 1 nanosecond, and low dark current, 1 nanoampere. Dark current arises from the surface leakage current as well as the generation recombination currents in the depletion region in absence of illumination. Figure B is a structure of side illuminated parallel to the junction PIN photodiode. This is the figure B. The side illuminated structure, figure B, where light is injected parallel to the junction plane, exhibit a large absorption width 500 micrometer and hence is particularly sensitive at wavelength close to band gap limit 1.09 micrometer. where the absorption coefficient is relatively small. The figure shown here is about the planar indium gallium arsenide PIN diode. Figure A is a structure and figure B is the energy band diagram showing the homojunction associated with the conventional PIN structure. A typical planar device structure is shown in figure, which requires epitaxial growth of several layers on an N-type indium phosphide substrate. The incident light is absorbed in the low-doped N-type indium gallium arsenide layer, generating carriers, as illustrated in the energy band diagram in figure B. The discontinuity due to the homojunction between the N-positive ion indium phosphide substrate and the N indium gallium arsenide absorption region may be noted. These are the regions which I have just discussed. This can be reduced by incorporation of a N-type indium phosphide buffer layer. Indium phosphide, this is the buffer layer. So going to the next slide, this is the figure about the substrate entry of indium gallium arsenide PIN photodiode. This is a structure. The top entry device shown in figure A is the simplest structure, with the light being introduced through the upper P plus layer. However, a drawback with the structure is quantum efficiency penalty, which results from optical absorption in the undepleted P positive region. In addition, there is a limit to how small such a device can be fabricated, as both light access and metallic contacts are required on the top. To enable smaller devices with lower capacitance to be made, a substrate entry technique is employed. In this case, light enters through a transparent indium phosphide substrate and the device area can be fabricated as small as may be practical for the bonding. The substrate entry PIN photodiode is shown in figure A. The device incorporates a P-positive indium gallium arsenide phosphide layer to provide a heterojunction structure or Schottky barrier, which improves the quantum efficiency. Moreover, it is fabricated in a mesa structure which reduces parasitic capacitance. Unfortunately, charge trapping can occur at the N-negative P-positive indium gallium arsenide or indium gallium arsenide phosphide interface, which may be observed in the energy band diagram of figure B. This may cause limitation in the response time of the device. However, small area substrate entry devices can be produced with extremely low capacitance, less than 0.1 picofarad. Quantum efficiency between 75 and 100% and dark current less than 1 nanoampere can be seen. So these are the energy band diagram for charge trapping, and this was the structure. This I have already discussed. The structure of a mushroom waveguide photodiode. A photodiode containing a waveguide structure shown in mushroom waveguide can however be used to overcome the bandwidth quantum efficiency trade-off between the device capacitance and contact resistance. The structure is illustrated in the figure. This is a structure for a mushroom waveguide photodiode. So these are some of the things. This is P electrode, this is polyimide semi-insulating indium phosphide substrate. Now the speed of response. The main factors limit the speed of response of a photodiode are the drift time of carriers through the depletion region. The speed of response of a photodiode is fundamentally limited by the time it takes photogenerated carriers to drift across the depletion region. When the field in the depletion region exceeds a saturation value, the carrier may be assumed to travel at a constant or maximum drift velocity Vd. The longest transit time T drift is for carriers which must traverse the full depletion layer with W and is given by T drift equal to W by Vd. So this is the equation. for the first. Now the second one is diffusion time of carriers generated outside the diffusion region. Carrier diffusion is a comparatively slow process where the time taken t drift for carriers to diffuse a distance d may be written as t drift equal to d square divided by 2 dc, where dc is the minority carrier diffusion coefficient. This is for the second, and this is for the third. Time constant incurred by the capacitance of the photodiode with its load. A reverse bias photodiode exhibits a voltage dependent capacitance caused by the variation in the stored charge at the junction. The junction capacitance Cj is given by Cj equal to epsilon S into A divided by W, where epsilon S is the permittivity of the semiconductor material and A is the diode junction area. Hence, a small depletion layer with W increases the junction capacitance. Now we go to avalanche photodiode. This is a type of photodetectors with internal gain. So this is the diagram for the APD. These are the various regions. This is the electric field. This is the x-axis. We can see this the green region, which is pretty high than the rest of the type of photodiode. The second major type of optical communication detector is the avalanche photodiode APD. This has a more sophisticated structure than the PIN photodiode. In order to create an extremely high electric field region, approximately 3 into 10 to the power 5 volt per centimeter, as may be seen in figure. Therefore, as well as the depletion region where most of the photons are absorbed in the primary carrier pair generated, there is a high field region in which holes and electrons can acquire sufficient energy to excite a new electron-hole pairs. This process is known as impaired ionization and the phenomenon that leads to avalanche breakdown in ordinary reverse bias diodes. It often requires high reverse bias voltage 50 to 400 volt in order that the new carrier created by impaired ionization can themselves therefore additional carriers by the same mechanism. More recently, however, it should be noted that devices which will operate at much lower bias voltage 15 to 25 volt have become available. Carrier multiplication factors as great as 10 to the power 4 may be obtained using these defect-free materials to ensure uniformity of carrier multiplication over the entire photosensitive area. However, other factors affect the achievement of high gain within the device. So these are the points which I have discussed. There is a case of the thermal noise which gets multiplied, and it is associated with the receiver circuit. Then there is this impact ionization, then avalanche effect, and how the carrier gets multiplied, which leads to the gain of the photocurrent. So next we have the structure of a silicon avalanche photodiode APD with guard ring. In addition, excessive leakage at the junction edge can be eliminated by the use of guard ring. So this is the main use of the guard ring structure. At present, silicon, germanium and indium gallium arsenide APDs are generally available in this guard ring. So avalanche photodiode responsivity. We'll be discussing responsivity in terms of avalanche photodiode. Responsivity as described by R is equal to photocurrent by output power, which is equal to m into nu into E into lambda divided by hc, where h is the Planck's constant, c is the speed of light. And similarly, multiplication factor also plays an important role in avalanche photodiode as the carrier gets multiplied. M, which is equal to Im by Ip, is the output by input. Here output refers to the total output photocurrent after multiplication divided by the primary photocurrent before multiplication. So next we have the benefits and drawbacks of APD. So benefits: APD generally provides an increased sensitivity of between 5 and 15 dB over PIN photodiodes, while often giving a wider dynamic range of results of their gain, variation and response time and reverse bias. Now the drawback: fabrication difficulties due to more complex structures and hence increased cost. The random nature of the gain mechanism, which gives an additional noise contribution. Then the third point, the high bias voltage requires, particularly for silicon devices, 150 to 400 volts, which, although lower for germanium and indium gallium arsenide APDs, 20 to 40 volt, are similarly wavelength dependent. Now the noise in photodetectors. Noise plays a very important role in case of photodetectors of all the types that we have discussed. Firstly, the thermal noise. This is the spontaneous fluctuations due to the thermal interactions between the electrons and the vibrating ions in the conducting medium, and it is especially prevalent in resistors and room temperatures. The mean square of the thermal noise is given by the first equation. Thermal noise is also known as the Johnson's noise, and it is represented by the equation I and J is equal to square root of 4 kBT divided by RSH. Now the dark current noise. There is no optical power incident on the photodetector. Even then, a small reverse leakage current still flows from the device terminal. The dark current contributes to the total system noise. This is a combination of bulk dark current and surface dark current. The bulk dark current noise. The bulk dark current arises from the electron-hole pairs that are thermally generated in the p-n junction of the photodiode. The mean square value of the bulk dark current noise is the second one. This is the equation. Here a new term Fm, which is the multiplication factor, is added. Next is the surface dark current noise, and the mean square value of the surface dark current noise is represented by the third equation, which is I and D is equal to square root of twice Q IL into B. Next is the short or quantum noise. The quantum or short noise arises from the random nature of the production and collection of photocurrent generated electrons when an optical signal is incident on a photodiode. This is the equation for the short or quantum noise, which is twice Q IPH B Fm into M square, and we have this square root. Here Fm is the figure of merit and M is the multiplication factor. And lastly, the SNR ratio of the photodetector. SNR ratio is the signal to noise ratio of a photodetector. The amount of the received signal can be can have a ratio which can be found out from this equation SNR. It is the input photocurrent divided by all the input noises. That includes Johnson's noise or thermal noise, the dark current noises, and the short or the quantum noise. We have discussed about the detection process, its advantages and disadvantages, and also noise related to it. We have tried to include most of the important informations related to it. Thanks for being patient. Thank you for watching this video. For more info, contact us on Facebook at @Gogoi and my friend Abhijit Kakati, or email us at littlewits2009@gmail.com or abhijit.kakati20@gmail.com. Thank you all.